Hi everybody. So in today's episode of The Builder Explains, we're going to find out what a solid, a liquid, and a vapor all have in common. I'm Alex. Welcome to the Renaissance Builder. Okay, so now that dry intro, I was about to say something else there. That really dry intro is done. Let's get into this. So, you guys actually voted on this, at least a few of you voted on this, and you decided that this is the video that you would rather see first. So we're working on that now. Now, there's a few things that I need to explain before we get into this. And what we have is a basic glass jar, a cup of water, some ice in a nice insulated mug, Coca-Cola, and vodka. We're not drinking the vodka, unfortunately, but we are going to use it in some experiments. And this right here to my left, well, to your right, my left, is what is essentially an incredibly overpowered, for this situation, vacuum pump. So what we're going to be doing today is putting this jar under vacuum with whatever's inside of it and seeing how the different elements react to the vacuum. So the thing I need to explain first is that pretty much every single day you wake up, you're under pressure. Insert Queen song, Under Pressure. Anyhow, so yeah, every single day you wake up and work all day long, your entire life, you are under pressure. Now, what that means, or what I actually mean by that, at sea level, we are under 14.7 PSI of pressure our entire lives. So the reason that makes a difference is to understand that when we talk about pressure under the normal circumstances, we're talking about everything above 14.7 PSI. So if I tell you that your tire is under 100 PSI of pressure, it's actually under 114.7 PSI of pressure. The reason this makes a difference, and the reason I'm explaining this, is because if you take away atmospheric pressure, then you have space, or no pressure, otherwise known as a vacuum. Because we are under pressure, 14.7 PSI at sea level, all the time, that actually influences how the materials in the world, or in our universe, behave. So it comes down to this. The more pressure you put a material under, the more solid that material becomes. To break this down in a real simple way, the more pressure you put on a substance, any substance, the tighter the molecules come together. So if you start with molecules that are usually yay apart, yay so far, I'm saying yay so far, like in order to see this, you would actually need like an electron microscope or something, like see really small stuff. But the more pressure you put on something, the tighter the molecules become, the closer they get together. And the less pressure you have on something, the farther apart the molecules become. Now, this follows a very similar path as heat in those same molecules. So the colder a molecule becomes, the less it moves. And the less it moves, the little tighter they become. So if we use water for an example, liquid, the molecules are moving, it contains a good bit of BTUs, or energy. The molecules contain a good bit of energy, right? So they're active molecules, okay? And they're moving around and they're jiggling around. Well, the colder they get, the less they move. And the less they move. And then all of a sudden, we're so cold that we become a solid, aka ice, and they start moving a lot less, and the molecules become closer together, right? This happens with air too. Like anybody that's running a drag racer, or anybody that's like super tuning their cars, knows that cold air results in better performance because there's more molecules in the air. Anyhow, so the colder it gets, the closer the molecules get, and it snuggles down into a nice tight space, making a solid. Now, if you apply heat to that, then the molecules melt, the ice melts, and that's the molecules warming up and taking up more space. Now, eventually you apply enough heat and they become steam. Steam often becomes a gas, and that's when the molecules are like, yo, we need lots of room because we have lots of energy resulting in lots of motion. And that's what happens. They take up more space. As far as water goes, it's 1,000 to 1. So for every cubic inch of water, you get 1,000 cubic inches of steam. And that's just how much more space the molecules take up because they're just that much more active and they need more room to move. So that's the general idea of what we're dealing with in a real simplified version. We can do the same thing as heating and cooling the molecules by adding pressure and taking pressure away. In today's video, we're going to be taking pressure away. So, the way this works is by taking the pressure off of the molecules, by relieving that 14.7 psi, those molecules will have more space and more room to move. And as they have more room to move, they're going to want to take up that space and end up, the molecules start separating enough that they become a gas, or they, move from a solid to a liquid kind of thing. This effect has a different, well, that idea has a different effect on different materials. For example, if I put metal in the jar, then we would need a lot more vacuum before we actually manage to turn it into a liquid on vacuum alone. Whereas, putting water in there, you'll actually see it boil pretty quickly. So that's the generic version of how this works, how a vacuum affects a substance. In this instance, we have the four substances because I want to see what it actually does. For starters, we're going to prove that if we put ice in here, that ice should melt just under a vacuum. And then we add water, and that water should boil. But I want to know what the vodka does. I think my prediction is that the vodka is also going to boil, but it's also going to get really cold. Because vodka is closer to a refrigerated material than water is. And then the Coca-Cola. So I just thought that would be kind of interesting. If you boil Coca-Cola, eventually you boil off all the moisture and you're left with like this gooey substance. I'm predicting that's what we're going to end up with. By the time we suck all the moisture out of the Coca-Cola, we're going to be left with this real gooey substance. And we're doing that last because that's going to be fun to clean up and I don't feel like doing that in the middle of a video. So, let's get to it. Alright, so the ice thing, there's no reason it shouldn't work. I love these Contigo mugs. They're pretty awesome. And I guess what I'll do is reposition the camera so that by the time we actually start this, now I'm going to have to do it pretty quick because the ice is already starting to melt. I mean, go figure, right? So I'm going to monitor the pressure via my transducer here, and I'm going to move the camera closer so you can actually see what's going on. Test number 1 begins, and we are going to, you can see the ice there. See if I can spin this around, get a better view of the ice. So you can see the ice, and we're going to start the vacuum up. Now this is the first time I'm trying out this here chamber, so let's hope it works well. Alright, there it goes. Now right now as we speak we are at negative 14.6 psi. You can't see much, but if you look closely you can actually see the water starting to boil. And yeah, I mean the ice is definitely melting just a bit faster. I'm doing this real time so you guys can actually see how fast this ice actually is melting. Now, it's not knocking our socks off fast, but you can see the glossiness of the ice, the surface of the ice, so you can tell it is indeed melting off pretty quickly. And you know what? This also serves as our water demonstration as well. So right now that ice is actually maintaining that water at 32 degrees. Just there's like some laws of thermodynamics that go into that. But you can see that one chunk, that's definitely reduced in size. Yeah. So that's what happens to ice under a vacuum. Little anticlimactic. I mean, it's not like a knock your socks off reaction, but you can definitely tell it is affecting the ice. Get our plug out here. So, that was, like I said, didn't knock our socks off, but made an interesting difference. You could tell that the ice was melting, like causing an actual physical reaction and beginning to melt. Now, I also said, when we were pulling our vacuum, we got to 14.6 psi, not 0.7. And the reason we didn't get to 14.7, and the reason you're not going to get to 14.7 is because a perfect vacuum is almost impossible to reach unless you go to space. Which I wonder if space is even a perfect vacuum. I don't know. Interesting question. I might have to look it up. Anyhow, as I pull this jar under a vacuum, the pressures, like right now, it's 14.7 inside, 14.7 outside. So the glass only has to maintain its own structure under its own weight. Ooh, this got really cold. Well, duh, there was ice in it. Let's warm that up. All right. So when I put it under a vacuum, this glass container now has to hold 14.7 psi from trying to crush it. And if we start getting too close to a perfect vacuum, then it ends up collapsing the jar, and anyhow, it's not a good deal. So at this point, let's add the water and see if we can't get this water to boil. Camera angle engaged, valving it off, and starting the vacuum pump. All right, we are now at 14.6 psi negative, and look at that, the water starts boiling. Now again, it's not hot. In fact, it's actually getting colder. But you can see that the water's bubbling up and it's boiling. Now, it's not boiling, as I explained, it's not boiling because it's hot. It's boiling because the water is trying to fill the space that our vacuum is producing. So, we did successfully boil the water at negative 14.6 psi. Again, as I explained, reiterate, so this experiment you'll probably see on the internet fairly often. It probably wouldn't be very hard to find. But the whole point of this episode is to explain why it happens. Again, it's not that this is hot. It's actually kind of cold. It's not that it's hot. It's that when we put a vacuum, we are creating space. We are taking away 14.7 psi of pressure, creating a space that the molecules of the water then want to fill. So the molecules start spreading apart because they want to fill that space. And, well, it's essentially the same thing as boiling just without the heat added. Now you've seen it. So that's it for the water. Fairly normal reactions. Those are normal reactions. Now, mind you, that's the stuff I've been dealing with for the past 17 years of my career. Boiling water out of enclosed spaces. Because we do the same thing in refrigeration. When I build a refrigerant circuit, and I did the same thing with this refrigerant circuit, when I build a refrigerant circuit and I want to charge it first, I have to apply a vacuum to that refrigerant circuit for a good period of time. In fact, we have a special gauge called a micron gauge that measures the amount of moisture in that circuit, because if I leave that vacuum on, I will eventually boil out all that water. I can straight up remove the water from this jar with this vacuum pump. And in a system that's made of copper, I can't see whether the water's in there, so we use what's called a micron gauge to tell if there's any moisture in the system or not. So that I've been dealing with for the past 17 years. So this really, is interesting, because science is interesting, but it's kind of commonplace and it's not really all that exciting. Let's move on to the other stuff, what I think should prove to be at least more exciting. So we're going to see if I can do a better job of pouring this. We're going to put alcohol in here. Now, mind you, the reason I want to try this is because alcohol, we already know, evaporates at a faster rate than water does under the same pressure. So if this evaporates at a faster rate than water does already, and it actually acts like a refrigeration liquid because its temperature to pressure is a lot closer, or there's less latent heat involved in the whole process, then we should be able to activate the process, the boiling process, a lot sooner on this. So I'm predicting that we'll at least be able to make it boil quicker. Maybe a more violent reaction. Either way, the vacuum pump's going to get drunk. It's not really. It's not getting drunk. It's not drinking this. It's just a machine, but I thought it was funny. So let's get started with this one. All right, now we got our close-up cam, and shut the valve and engage the vacuum. And there you have it. As I predicted, a more violent reaction. Because of the lower latent heat value of the alcohol, the effect of the vacuum is much greater on this substance than on the water. So as I predicted, the reaction was much more vigorous with the alcohol. And the other difference it made is we actually brought down the temperature of the jar pretty drastically. So that's interesting. So far I'm 3-0 as far as my predictions go. All right. Now for the last one, we're going to see what happens when we do this with the Coca-Cola. And this time, I'm actually going to leave it under a vacuum for a while. Because I want to see, we're not going to put as much in here, and I actually want to see it turn to a sludge, if we can at least accomplish that. Alright, so I'm only going to put that much in, and I actually want to be able to pull this moisture out. So this time we might time lapse or skip ahead, or whatever we got to do. So we're going to put this under a vacuum. See, it should start doing the same boiling action, or at least it may not boil, but at least we'll start pulling the moisture out of it. And then we're going to let it run for a while and come back to it and see if we made the tar. Oh, got to shut the valve. There it starts boiling. Cool. so now we're just going to let it run for a while, and we'll come back to it, see if we can't make the tar out of it. Alrighty, so this is actually going to take a lot longer than I expected. So here's one of the things that you're fighting when you pull a vacuum on a substance, especially a liquid. When you start removing so everything, pressure is temperature related. It all links, so pressure temperature relationship. So when you start boiling a substance off by pressure, you actually drop the temperature as well. In fact, that's how a phase change refrigeration circuit works. Well, phase change, that's how a compression cycle refrigeration system works. Anyhow, so what we've actually done, and I'm sorry, but I kind of find this a little impressive. Now, mind you, it's going to take a lot longer in a few oil pump changes to get the moisture out of this to the point where it turns to a syrup, or back to a syrup. It would take longer than I really have time to put to it, because we don't want a video that long. But what I actually have managed to do, you'll notice that our jar is condensing. This sucker's cold. Like, I have turned Coca-Cola into a refrigerant. So as we remove the moisture out of the Coca-Cola, we drop the temperature of the substance that's left as a liquid form, and it's below, I'd say it's probably about 50-degree dew point in here. So it's below that, below 50 degrees. So I guess another way to cool down your beverage is to pull a vacuum on it. It's not practical at all, but it's a thing. Anyhow, pull that back in there. Guarantee you that stuff is flat, all kinds of flat. So that is our experiment in, man, that's cold. That is like very cold. Anyhow, that is our experiment in pressure changes and how they affect different substances. So as we figured, the vodka was going to have a more volatile, I say volatile, it wasn't that much more exciting, but it definitely had a larger reaction than the water. We did notice the temperature difference, like the change. This is evidence of it. I mean, we're condensing on the bottle. It's cold enough to condense. So we definitely dropped the temperature of the substance by pulling a vacuum on it. So we proved that. And, hey, we tried sucking down on different things. So in respect to the Builder Explains, now we've gone and showed what happens when you pull vacuum on different substances and explained why it happens. So we empty the space inside the jar, and now the molecules have to try and take up that space, and as the molecules go further apart, our temperature drops. So there you go. Now you guys know what the whole pressure versus temperature relationship is all about, and what happens when you pull a vacuum on water, vodka, and Coca-Cola. We turn it into a refrigerant. Isn't that something? And ruin vacuum pump oil in the process. So thank you very much, guys, for watching. Hopefully you at least found this at least somewhat entertaining, if not a bit informative. And I really appreciate you guys watching. If you like this video, go ahead and throw a thumbs up in there. Make sure you're subscribed and hit that bell icon for future Builder Explained videos and, well, the rest of the Renaissance Builder series overall. I thank you very much, guys, for watching. As always, you have a good night.
Bye-bye.